Alright, so today we'll be showing that Clique is an NP-hard language. In order to show that Clique is NP-hard, we'll show that a known NP-hard language, polynomial mapping reduces to Clique. Today we'll be working with Clique and independent set. And so we'll be using independent set, a known NP-hard language, in order to show that Clique is NP-hard. I've written the definitions of both up here just as a reference. And so Clique takes in a GK where G is a graph with a clique size at least K, and independent set takes in a GK where G is a graph with an independent set of size at least K. And so in order to show that independent set polynomial time mapping reduces to Clique, we'll need to map instances of independent set to instances of Clique and non-instances of independent set to non-instances of Clique in polynomial time. And so we'll construct a function f in order to do this. And so before we write out a function f, we need to come up with some intuition as to how this mapping works. So I've drawn up some graphs over here just to take a look at to help us understand how independent set and Clique are related. And so if we take a look at this graph up here, we can see that this graph has an independent set of size 3 because these three vertices share no edges. Note that in this graph down here, this graph has a clique of size 3 because these three vertices all share edges. They're all connected to each other. And so if we look at how these two graphs are connected, we can see that for every edge in this graph, we didn't put that edge in this graph. And for every edge that doesn't exist in this graph, the edge is in this graph. And so if we take a graph like this and we draw an edge between all vertices that don't currently have an edge, like so, we're able to construct this graph that has, instead of an independent set of size k, a clique of size k. And so based off of this intuition, we can now construct our function f. So on an input, gk, we need to map instances of independent set to instances of clique. And so we'll want to construct a g prime that has all of the same vertices as G. So V prime will equal V. But for the edges, E prime, we'll want all edges that are not in G to be in E prime. So we'll say that E prime equals an edge UV where U and V are both vertices in V, and the edge UV is not in G. Okay, and so based off this, we can now return our G prime. So we can return Alright, so we can return our G prime, which has the same vertices as G, and the exact opposite edges as the edges in G, as well as the same K value. And so, now that we've constructed our function, we want to do an analysis of whether or not this works as intended. And so we can see that if a graph has an independent set of size K, then we know that there will be at least K vertices that share no edges. And so when we construct our G prime, we will have a G prime that has at least K vertices that are all connected. And so therefore G prime will have a clique of size at least K. If G and K are not an independent set, then there will not be K vertices that all of which do not share edges. And so when we construct our G prime, we will not have at least k vertices, all of which are all connected. And so therefore, our G prime k will not be in Clique. So therefore this works as intended, and we can finally take a look at efficiency. So this first step, creating V prime, is O of V, and the second step is O of V squared E. And the final step is O of 1, so we can see that all of the steps are in polynomial time with respect to the input gk. And so we've been able to polynomial time mapping reduce independent set to Clique, and so therefore Clique is NP hard. Thank you.